Yes. Okay. So say we have, this is about the fact that if we have, it's multicollinearity, right? That's where we crashed and burned last time. That's what we were talking about last time. So when predictors are pairwise perfectly correlated, you have a dependent set of predictors, but that's not really going to happen usually. And if it does, there's an easy fix for it. You could just combine them into a single predictor because there's a definite functional relationship between them. So that's not really what we're worried about. We're worried about when the entire set shows dependence, which does happen often. If you have a lot of predictors, or even not that many, few, there's a good chance that you can get pretty close to writing one of them as a function of the others. Well, it depends on how many rows you have too, but anyway, this situation can happen, and it does happen. And what do you mean by close? All this stuff gets very involved, but still the overall effect is common and something everybody has to deal with. So that's what we're talking about. And just try to give a quick demo here of this, and then explain it a little in the notes, and then we'll continue with the next stuff. I don't know, this will take part of the class today, but not all of it. So yeah, so okay, so what do we want to do for the notes? You're seeing the R console, right? I think. Okay, yeah. So let's build an X matrix. So let's say I have X1. So these are the predictors, and I'm going to pick enough rows so that nothing, so that it's kind of real, and also so that when they're not too dependent, you can see it's a reasonably good model. So let's make this normal. So I'm going to go R norm, and I thought of 40 would be good. 40, and let's make the standard deviation 3, say, and let's just make it this. Okay, so we'll just make it perfectly normal, distributed, and let's say X2 will be this, and let's make it 2, and let's add a little bit to it. I just thought of this just randomly. It can do almost anything. Now let's take X equal to C bind, and we'll put the ones in here. So 140, that's my first column. This is my data matrix. I'll put X1 here, X2 here, and let's put something that's sort of related to X1 and X2, but maybe a little bit of noise. So we could do something like, let's just say X1 minus X2, and maybe add a little of the first column, or a little constant here, or maybe add a little bit of another normal. So I'm going to do 0.2 R norm. I think this will work. It'll do it element-wise. In other words, it will create the R norm vector and give it a small, make it pretty tight around 0, and kind of offset it a little. So it's not perfectly dependent, but somewhat close. Okay, does that make sense? This should sort of do it, I think. Let's try it anyway. Hold on, did I not? Got to put the times in here, right? Okay, now, okay, so that's my X matrix. I expect this to it's going to have full rank, but I expect it to be close to being, those columns are pretty involved. I mean, we could look at the correlation of the columns, but if you think about it, yeah, I mean, column 4 is the one in issue. It might not really be perfectly correlated with X1 or X2, but with the combination of them, it's highly correlated with the combination of them when it's X1 minus X2. So you got the thing with those three seem correlated, or seem seem dependent or close to dependent. A little bit, there's that little bit of noise to make it so it's not perfect dependence. Okay, so let's look at the eigenvalues of x prime x. Let me see. So let's just see if this is what I want to show you first. Look at my notes here. Yes, first I want to look at this, right? First we want to look at the eigenvalues of x prime x and look at this matrix. So let's look at M. Let's call this x prime x. We know this is an important matrix for computing the coefficients, right? For computing B, and it actually appears in everything. Right? It appears in the inferences about y hat, the expected value of y at different levels, new observations, and the coefficients. So we'll just call that M, and let's look at the eigenvalues of M. So M is square now, and so it can compute the eigenvalues. And there we go. We got I just made this up, and we have 1 is 1,000 about. That's kind of interesting. The eigenvectors are guaranteed to be orthogonal by the spectral decomposition because M is positive, definite, and symmetric. It's called the spectral theorem and the positive definite theorem from linear algebra, Math 130. So I guaranteed to get these. Every time I do this, I still just always feel a little bit of wonder about this, that I see always positive eigenvalues and orthogonal eigenvectors. Now, what do you think is the interesting thing about the eigenvalues? By the way, I'm not looking at any of you, so if you want to say something, just speak up. Or see this giant coffee cup?
Maybe it's how spread out the eigenvalues are.
Yeah, it's how spread out they are. That's right. So, and actually the one that they're actually at all these different levels, orders, right? You have one like third order, second order, first order, if you like, and then -1 or something. So, but this is the one that's the problem, is the little one here. Because you remember, it's really the inverse of M that I'm using to multiply. And when I take the inverse of M, the eigenvalues are the reciprocals of these. So let's just like put that in just so we can see that. So put in solve M here and see what and you see, you have these very small eigenvalues here. And that's good, really, because those relate to the variance of the coefficients. So you have low variance for the coefficients, a lot of accuracy in your coefficients, and that carries over to the inferences about the expected value of y and those other things too. But here, even though 2 isn't a huge number, when you compare it to these, it's pretty big, and you're going to get some error from MSE too. And this is going to like double it and stuff. And you want it to kind of have this reducing effect here, but it's doubling it. So this is the problem here. Okay, so I'm already seeing the problem. I'm relating it to the eigenvalues. If I have a small eigenvalue in comparison to the others, anything less than 1 really is going to tend to inflate the variance of your model, of this model. So here's what I'm going to do. I feel like I'm running off the screen here, but you can see everything on the screen, right? If somebody doesn't, please just speak up. Okay, but so let's run the model now with this. Okay, I have X. I got to kind of bring it into a model notation. The only thing is the X3, I didn't name that. So let's call X3, how should I name it? I don't want to call again R norm 40. It will do a new R norm 40, but I can just access it from here, right? It's just X. I want all rows, and I want column 4 actually because of the ones there. So that's X3. Okay, now I can save the model as mod equals LM. Oh, I don't have a Y. let's make a y. It really doesn't matter what we call y. So let's set y equal to maybe another normal. 40. We could offset this a little if you want. Let's say plus 0.5. I'm making this up. And r unit 42, just to throw it off a little bit. But I don't think it actually even matters what y is, come to think of it. But just so we can have a model here and get coefficients. So yeah, so now if I do the lm command, I'll save it mod equals lm. I hope you can see the screen. Please interrupt me if you can't. I'm not looking at anybody so that I can see. So lm y squiggle x1 plus x2 plus x3. I don't need to put data, right? Everything's just defined here like this. Summary mod. Okay. Yeah, it's bad, right? And you could see actually like the p-values are worthless. Basically, you have no significance essentially, except for the intercept, which isn't even part of a regression model. So yeah. One thing I look at a lot, I don't even look over here at the t-value thing, but just look at the standard error compared to the estimate. The standard error is bigger than the estimate itself, sometimes many orders. So you're not going to get something reliable. You don't even know, like you don't know. So it's estimating these right around 0, but you have like nearly a 1 unit standard error. A pretty useless model. The R squared isn't very good either. That doesn't necessarily have to be the case. I think if I ran it again, maybe I took not with this, nothing's going to change if I just type LM again. But if I redid this with, these random generations, I might get something with a better R squared. That's not necessarily going to be terrible, but the significance of the coefficients and the other stuff is going to be bad. You can see the p-value, the overall p-value is not good. And this is what you get. Okay, so just to test let's test the model now without that troublesome fourth column, right? We thought maybe we were helping by adding this fourth column, which granted I made up rather than get it from data, but this is just to show you what's going on. So let's take that fourth column out and repeat. So let's take X. I'm going to just overwrite everything. So I'm going to say X equals X. I want all the rows, but now I want columns only 1 through 3. To get rid of that last column. Notice that's going to be gone. No, I saved it so that I can still get it back if we want to talk about it. So that's X now. So let's let M again. I can just up arrow and I'm going to look at the actual matrix and all that stuff now again for this one without that problematic fourth column. And let's look at eigen M. You notice these changed, they all changed, but none of them are below 1. And even though this one's a little small, showing maybe some dependence but on the other 3, it's only 1 order off, not 4 or whatever that other one was. Okay, and if I do this, of course, the 26 is going to be the only one that's a problem, but it's not really going to be a bad problem. So yeah, all the variances reduce are less than 1. That will have a reducing effect on the variance in the B, and then carries over to everything else. So everything looks good now. Everything looks good. So now let's do this model. So if I type mod again equals LM, I'm going to keep the same Y, and let's put in what was it? X1. You don't have to put the 1s in. That comes for free. There is a way to take it out. We haven't talked about that if you want to take it out. But let's just look at this and summary. And I up arrow, which is faster, up arrow. Wow, not that good, right? I thought it would be better, but it is definitely better, but still not great. Yeah, like I said, well, it's definitely better. You can see it, this one is almost significant and this is more reasonable. It's kind of getting closer. It's still not very good. It's funny, the one I did before, when I was just doing this on my own, just to make sure I wasn't forgetting anything, these were now suddenly had 2 stars like next to them, these two. So it just shows you that you are taking random samples and you're working with unknown effects sometimes. So they are still somewhat correlated here, somewhat dependent, but somewhat not a great model still. But I'm not really sure what happens. We could try the whole thing again. I'm actually not scared to do that. Let's try to do the whole thing again, but just with the reduced one maybe, and see what we get. So what did I do here? X1 was this. X2 was this. Now let's see. Yeah, what the hell? And let's just try it again. Yeah, let's just try it again. So if I go this now, maybe it's just not as good as the one I did before. Yeah, it's even worse, huh? Still, it's not as bad as the other one. I'm just gonna have to go with that. The relationship is a bit complicated, but so I shouldn't have done it, right? It would have looked better if I didn't do it. The relationship is a bit complicated. Here, I'll tell you what, I did save my output, so I'll show you what I got when I did it before. Here, let me see if I did something different, maybe. No, I did exactly the same thing. And I got this. So let me just show you. Hi, Claire. So here I was doing this similar thing. Let's go up here. Maybe you can spot it. Here, I think it just might be just randomness though. Here I took x1 equal this, x2 equal this. Maybe this one was different. And then I combined it, right? Blah, blah, blah. Go down here. I get similar thing here and bad model. But then when I reduced it and did it here, I got this model. So these were very significant here and good. And so with really, I don't think I did anything different, too much different. Maybe the Y. That's the bad one. This should be the good one. Anyway, one thing I can tell you, you're guaranteed to get crap if they are dependent, highly dependent. If they're more moderately dependent, I think it's more you know, less certain what could happen. You know what? I'll even say if they're even if they're highly dependent, there's a chance the model could look good. But it is somewhat complicated in that respect. So there's a lot, it goes a lot into this this subject. It's a very practical problem. It talks about this a little in chapter 10, and we'll probably have one more class on this topic because it's probably the most important one in multiple linear regression. And but that's pretty much gonna do it. Okay. So let me show you a little bit of any questions? Yeah. Okay, so let's now let's see what's going on. All right, let's see if I can write. Yes. Okay. Okay, so the first thing I did want to go over that relationship between this and just show you the, it's because I'm over here. Okay, yep. So this was from last time we talked about this. So if I have my data matrix X, we said if the rank of X is less than P, that's true if and only if XTX inverse DNE. One implies the other, okay? So if you do have something that is truly linearly dependent in your data matrix, you can't even take the inverse anyway, so you get no model. And the same thing, if you start with X prime X inverse and you see you can't take the inverse, well, that means your data is linearly dependent, perfectly dependent, and that means there's a fix for it, really. You can find the columns that are dependent and combine them into one column. I'm not sure it will be a fix in the practical sense, depending on what kind of statistics you're doing, but at least you could do something and proceed. You can combine those columns, get a smaller model, and then do your regression. So anyway, let's just do the proof of this. And I think the one thing I wanted you to show to convince you is that if this is true, what does this mean? This means that there exists some vector C in RP, actually, right? In RP, not equal to 0, some non-zero vector, so XC equals 0, right? That's what that means. And the same thing, if you have a square matrix and it's not invertible, that means the columns are dependent. So this also is just another name for this same thing. So this is just there exists C in RP again, C not equal 0, so that X prime X, if you like, we could put that equals 0. I can find the linear combinations of the columns of X or of X prime X that give me 0, besides taking 0 times all of them. Okay, so let's show this one then. So the proof of this, because this, although this is not really part of the course, you wouldn't be asked to prove this. This is really good to know and just to be confident of this. It helps you in this. So let's assume, let's assume this one and then show the right one's true. This one's the easier one. So if this is true, then we know. So we know. So we assume, so there is C. So XC equals 0, right? But then, so that's the assumption. Then I can take X prime times XC, which is just equal to 0. X prime times 0, which is equal to 0. But this is equal to x prime x times c is equal to 0, and you're done. So in other words, the same c works. Okay, so the same c works. So if you have a c where this is equal to 0, then that same c, if I put that into x prime, if I multiply that by x prime x, I also get 0, so you're done. So that one's not hard. What about this way? So there is c, there exists c, so x prime x times c equals 0, and we want to show that means xc must equal 0. That's not as obvious, right? Not as obvious, but still not. There's just a simple trick for this. Maybe not simple. It's not as obvious. Okay, the trick is to multiply both sides of this equation by c prime. So we can say then, right? Just multiply both sides by c prime. So c prime x c must equal c prime 0 equals 0. But what is this? This is just xc prime times xc, which is just the length of xc squared if you want. Okay, so this implies the length of xc equals 0. What does this imply, though? What vector has length 0? Go ahead, tell me, speak up if you want. Take a chance. I'll edit it out for the video. No, I'm kidding. I won't edit it out. You know me. I would not edit. I don't know how. The only vector whose length is 0 in the Euclidean world. Yeah, 0, right. So it's the sum of the squares of the elements. So this implies xc is 0. And c, since c is not 0. So yeah, up here I should always write this, c not equal to 0, c not equal to 0. Of course 0 is true. This implies xc equal to 0 for c not 0. So I don't even have to write that since I fixed this up here, which implies rank x less than p. If it had full column rank, all the columns were independent, then I couldn't say that. Okay, so you know one implies the other. If your data matrix has independent columns, you can take the inverse of x prime x. If not, you can't. That's nice. Okay, so we're always going to work in the world where we can. If we can't, we're going to have to fix it to do any kind of regression. So let's assume, so let's continue a little more and just look at, I'll write the title of this. Well, it's only one word's been written, so I could. So the next thing is, suppose x has nearly dependent columns. What do we mean by this? If I took a linear combination of the columns, I could find a linear combination of the columns that come close to 0 without that is not multiplying every column by 0. So in other words, I can almost satisfy that definition that there's a vector C that xc equals 0, but it's not quite 0, but it's very close. So if I can do that, I still get this effect on the model. So what is the result? I can just tell you the punchline right now. It makes the model unstable. You have high variance in the coefficients, and that carries over to everything else. Okay. So X has nearly dependent cols. So we'll suppose they're not exactly dependent. I'm going to have to write all this since I'm saying it too. So, so let's say I'm going to write it anyway. I can't help it. X prime, X inverse exists. Which implies then that X prime, X is symmetric. I could just said the columns are independent. This implies X prime X is symmetric and positive definite too. And if you don't know this stuff, it's okay. But if you do, it's good to know. And so this implies there's this thing in linear algebra called the spectral theorem that the eigenvalues are positive and the eigenvectors are orthogonal. So this implies that there exists that X, let's just say it this way, X prime X is equal to Q lambda QT, where lambda has the eigenvalues. I don't intend to teach this. I'm not teaching this now. So if you don't know this, it's okay. Just ignore it. And so then X prime X inverse would be equal to the same eigenvectors. This is inverted. And here I have lambda equals the reciprocals of these, 1 over lambda 1, 1 over lambda p. And this is the one we care about. So if I have a small eigenvalue here, this means I get a large eigenvalue here. What happens then? If I multiply a vector by this that is in alignment with the eigenvector that corresponds to the large eigenvalue here, let's say it's 1 over lambda p is very large, and I multiply something that's close or has a lot of the pth eigenvector here component in it, then it's going to super magnify that vector by whatever this is. A little less than this because it will have other components probably. It won't be exactly this eigenvector, but it's going to blow it up, and that's a problem. And that's what you're seeing there in the LM command. It comes out that way. So let's just write a few words, and then I'm basically going to say that's it for now. And we'll see this again a little in chapter 10 coming up soon. So suppose lambda p, 1 over lambda p is large, is big. Okay, and say X prime Y has a large component of QP. Okay, well then X prime X inverse times XY will be large, be big. In other words, something that's independent of the x's here, this xy, depending on what it is, I could get something very big. But if y is something else, I could get something moderate or even very small. So we could say, add another sentence, we could say, whereas if x, this should be a prime here, if x prime y doesn't have much component of large corresponding to large evals from then may not and probably will not. Okay, so what this means is there's a lot of variance, a lot depending on exactly what y is, what the data is, in what could be your coefficients. Your model's not reliable. Okay, so I know this may be just pushing it over the edge a bit. This is not why I wanted to do this online. I wanted to come in and do this in front of you, but it was just a little overwhelming to deal with the snow, the ice, and the street. I could have done it. I didn't really want to. It's not always so fun driving in Worcester in the snow. Have you noticed this? It's a little dangerous. Okay, let's see. The parking too. Let's see. Was there anything else to say here? Like if you were going to do more on this, what you could do is actually find those Q vectors and then pick y equal to the Q4 vector, that perfectly lined up with that eigenvector, and you would see it blow up and the model would be demolished basically. But I just figured, well, there'll be some of that one in there, but there really wasn't that much with this example compared to the one I did earlier this morning. Any questions? Okay, look, let's keep going a little. I want to stop at 4, but I think we can keep going. We've got about another 25 minutes. So if you can hang in there, we'll at least start the next section and go to a little bit of a happier place, maybe in the next section. We will look at this again a little bit coming up in the model building part. Basically, my thinking is 1 or 2 lectures on model building, especially chapter 10, if you want to read ahead. And then we're going to talk about nonlinear models and logistic regression for the next 4 lectures. Okay, and that will do it. I think we only have 6 left, really, or 5 even. So something like that. Okay, in case you want to read ahead. So chapter 10, 13, and 14, but just parts from them. But if you're interested, you could start to read ahead. Okay, now I just want to talk about chapter 8 here and on polynomial and indicators. So polynomial regression. And the big takeaway from this is that there's not very much to learn here. I think you almost don't need to worry about this very much. So we'll just talk about it, though, that it's familiar. There are a couple things to mention, but it's basically just a new case of MLR. So I'm just going to write these notes down since I'm talking a lot. One predictor, say we could have a model like this, yi equal I don't call it 2, xi1 squared here. It's the same column. Okay, so this is my model, usually going to assume the normal error just like before. So here, what is p equal to? P is 3, just like before. The big takeaway here, just like MLR3. So just like MLR 6.7. I just think of x squared as a new column. There is one thing, though, with this particular one, might not be true for others, but we usually do this for a quadratic, is because if you think about it, if say you're over in the positive numbers somewhere and you have a quadratic fit and you have a linear fit, you get high correlation, high core for short. We do a centering, which is a good trick and can't really hurt. So we usually write, the book writes it like this: little xi is equal to xi minus x bar. Oh, I'm calling it 1 here. Yeah, we could call it 1. And we would usually do this. So this prevents, to prevent multicollinearity, to prevent correlation between x and, say, x squared. Okay, and then, so then the model would still be yi not transformed equals beta 0 plus beta 1 xi1, that's a lowercase xi1 plus beta 2 x. So we can call this beta 2. Yeah, let's call it beta 2 xi1 squared plus. Just center it. You could even divide by the standard deviation too, but you don't need to if you just want to get rid of the correlation. Now, let's look at something. If you want to go back to return to your regular estimated coefficients, then let's say we try to fit this model then. So let's say we fit this. We get, I'm going just to write less. I'm going to matrix note or vector notation. So we get y hat equals b0 plus b1 x plus b2 x squared. And I don't have to write the error anymore. And now let's, we fit this, right? So fit this with LM. And these are the lowercase x's. Remember, if you're watching this later or for the first time, it's work. It's not supposed to be as good as watching your favorite band on YouTube. So what you got to do is just pause it a lot, slow down, take the notes, and you did your work. Okay, so what is this? This is equal to B0. Let's put in the original stuff here. Same y hat. Oh, running out of space. Got to add a new page. Okay, hope that's enough. Okay. Okay, equals. Now multiply it out. Get out of here. Multiply it out. What do I get? So any constant terms? Yes. The x bar is constant, right? I can rewrite it out in terms of, I just want to write it out in terms of x and x bar. So I'm going to bring the x bar over to the B0. If you think about it, x bar is just a single number and it can go with the B0. So I have B0, here's my big constant term, B0 minus B1 X bar minus plus B2 X bar squared. Now, how many linear terms? There's plus B1 X and then minus 2X bar B2 X. We can put these together. X and then just plus B2X squared. So the new, in terms of the original, sorry, I want to get that guy in there. We can call this B0 prime, B1 prime, say, and B2 is equal to, I think, B2 prime. Yep. So this shows the relationship. So these B0 give the coefficients in the original variables. Any questions? Now, I could go to a two predictor polynomial regression, and you could go to also higher orders. You could have cubes, fourth power. This is generally avoided because what can happen is your derivatives of these things are much higher, so you can risk missing things as you go, because the change in the regression function is more subtle, more delicate and sensitive, and you get out of scope a lot faster, all these things. So generally you try to keep it low, 2, maybe 3. If you wanted to do 2, let's say, you would just put the squared one in. If you'd go to 3, you would put the cubed one in, but you always include the squared term too. You rarely would have something with, like, say, a constant term beta 0, beta 1 x, and then just skip to beta 2 x cubed. That has problems associated with it. It might fit well for the data you have, but it's subject to problems if the data were to change slightly, and it's generally considered a bad practice. So generally just remember that rule. You might notice if you're taking ODEs or something that there's a similar thing with differential equations too, where you fill in lower ordered terms when you do that. I'm not writing any of this down. Okay, so that's that. I think the next thing to look at is, otherwise everything's exactly the same, okay? And you have a few homework problems added about this for the next homework, and you'll get practice doing it, but there's not a lot new. Okay, next thing is interaction terms. If I go to two predictors, I can look at, say, how do the two predictors interact? Do I want to represent that? Like, in other words, you have something where each predictor influences Y, but they, as a team, they really affect Y. Okay, there's something that happens when they're both added to the model that needs to be accounted for. So one thing we can do is, common trick, although this isn't the only thing, is to just multiply the two things, and then we get like a reinforcement new predictor that's a reinforcement term, or a if they sort of cancel each other, a canceling term. So let's just write this down. Here's a two predictor polynomial model with an interaction term. But really, you don't have to learn much. If you're short on time, you can think, well, I don't have to do too much here. Okay, so this is yi. I don't like writing all the y's, so let's just do it in vector notation. Also, there's two ways you could write. You could write e of y and then just take the error term off. So let's just write this for now. So e of y equals, I'm switching it up. I hope that's okay. That is, makes it a little easier to write. Beta 1, x1, beta 2, x2. Oh, one thing is the book and other places sometimes go to this double notation too. So we'll do it this way. And then plus beta 1, 1, x1 squared. I can think of the 1, 1 because it's x1 times x1 plus beta 2, 2, x2 squared, and then plus the other quadratic term. Don't forget, there's another one, which is both of them. Beta 1 to x1 times x2. Okay, and I could have wrote that yi equals these and wrote all the i's and wrote plus epsilon I. It's the same thing. There's nothing new. I do want to center these two because it has the quadratic terms and the linear terms. Okay, so this is p equals what here? How many parameters do I have here? I'll let you think about that. And then we also want little x equal to, or let's say little x, let's say little xj equals xj minus xj bar. The big ones, I want to center them, and this is to prevent the correlation again. So j equals 1, 2. So how many parameters here?
6.
Yeah, very good. 6 parameters here. Nothing new. If you're trying to build one of these models, you just multiply your columns like this and square them, and you can go. Center them. If needed, maybe not needed, but probably needed. Probably would help. Okay, one approach, I'm not writing all this down, but one approach is to know what model to do is to pick the highest one you want to deal with, maybe quadratic, maybe cubic or something, and then reduce it using partial F tests and extra sums of squares. In other words, all right, do I really need the cubic term given I have the interaction terms, the quadratic terms, and the linear terms? And do your SSR, your extra sums of squares, F tests, and take them out one by one. If I put cubic terms in there, there's a lot more terms. So with two predictors, there's now a lot of interaction terms. I can't even think, right? Because there's x1 squared and x2, and then, I don't know. Maybe if you just want the quadratic interaction, but the cubic, single ones, anyway, it grows fast, and it's really kind of, especially just in this course, it's a moot point because you're probably not going to be doing this, at least not right away. And if it's not even actually that big a deal, so you could figure it out when you get there. Okay. Little more, and we'll continue probably next time with this stuff. So, yeah, why not? Let's just go a little more. Yeah, the plan was to do this and then also indicator variables too today, but that will be next time. So we'll just sort of deal with this. What the book calls qualitative predictors. We'll start that next time. But let me just do a little more about the interaction effects and then we'll stop. Okay, so say we have the simplest thing. So we have, let's do an example. So say we have, yeah, let's just write this out first. Interaction effects, and then we'll do a quick example. So let's call this star here. Okay, so say x2 is held constant. Let's just write these cases out. You can help if you want. Please volunteer. I feel more relaxed now. We're just going to do this. So x2 const, and say we increase x1 by +1. Then EY does what? I'll say EY just to buy time. EY increases by, and by increase, I mean changes, or I'm going to say increase, but it could be a minus amount too. What happens to EY if in that model up there, I hold x2 constant and I increase x1 by 1? What is the change in EY?
Beta 1.
Beta 1? Yep. Beta 1. Anything else happen?
You have your two other terms.
Yeah,
with
the other.
beta 1 in it.
Yeah, right. So I think what would happen if I increase, so yeah, this one, yeah, it does depend on this term a little bit, huh? This is the one that's kind of bothering me. I didn't mean to put this in this example. Let me change it just to make it simple, because I could do that. We could do this. But it wasn't the one I want to do. So let me just let's take this out and just make it a little simpler here. Let's say I'm going to say we don't want the pure quadratic ones, but we want the interaction ones. So say we have in EY equals beta 0. And I'm also giving you time to think about this. Beta 1 x1, beta 2 x2. And let's just take the interaction term, beta 1, 2, x1, x2. Okay, now say I increase x1 by 1. What would the left-hand side change by? Well, like this is still going to be the same. This is going to change by, since x1 goes up by 1, this is going to change by b1. This is going to stay the same if x2 is held constant. This one is going to change, right? And it's like x2 is a constant, so instead of going up by beta 1 or beta 1, 2, it goes up by beta 1 times x2. So let's put this in. EY increases by, and I don't know what this is, but let's say beta 1 plus beta 1 to x2. And if x1 is constant, and we increase, say, x2 by 1, then EY increase by, you want to try? By beta 2, right? Plus beta 1 to x1. All right, so you can see with the interaction terms, the increase in your predictor on one thing will involve the other predictor. Or I mean, yeah, it will involve the interaction coefficient, but it will involve the other predictor. Yeah. Let's do a numeric example and look at it. So to see a numeric example, say we have EY is 10 plus 2x1 plus 5x2. And we want to consider EY versus X1, say EY versus X1. How do I plot this? Well, you can't in 2 dimensions, but we could look at it at like a couple levels, say at X2 equals 1 or X2 equals 3. And just draw 2 different lines. So I'm going to have a little graph here. And this is EY over here, the response. Down here, I have X1. And how does EY change? Well, it's based on this really, right? If X2 is 1, so for this one, then we have EY equals 2X1 plus 15. And if X2 is 3, then we have EY equals 2X1 plus 25. And yeah, so we get slope of 2, that doesn't change, but we have a different intercept for the expected value of Y. Okay, so something like this, right? Something like this is if X2 equals 1. Okay, now say did I get this right? Yeah, for this model, right? This doesn't have an interaction term. Now let's do one with an interaction term. So example B. So we could say EY equals 10 plus 2X1 plus. Okay, I don't have any, I can't figure out how to add a page in. It's okay. Oh, I see. Yeah. Let's see. I think we can do this anyway. So say X2 equals 1 again. So say at X2 equal to 1. EY is just equal to, well, I get the 15. But the linear term changes. So I get the 15 again, but then I get plus 2.5 X1. And then at X2 equals 3, EY equals 25, I think. Yeah, 25 plus now 3.5 X1. So the slope changes too. And so we get something like this. Okay, so the slope is 25, but it's increasing faster, so it's maybe like this. This is if X2 equals 3. Here's EY over here. Here's X1. And let's see, this would be down here. I'm not sure where they'll cross over, but hell with it, I'll just guess. So say something like this. Let's see, if we put X1 equals 10 in, what do I get? I get 60 and 40. So yeah, if it's 10 here, they're off by 20. At 0, they're only off by 10. So they'll be off by, they'll cross over here on the negative side somewhere, probably further over here though. Okay, anyway, this is just to show you there's more going on with these kind of models, right? You got to be careful when you analyze them. And this is another argument, sort of as we close, for not making them too complicated, especially you don't want to go too high, the order's too high or the interaction's too high. They sort of defeat the purpose of having a model in the first place. They get too hard to communicate and understand. All right, look, I think that's good. I'm going to stop. And does anybody have any comments want to go on the record before the recording's off? Like Congress? Okay, I'm going to stop recording and stop sharing soon after that.